To illustrate the capabilities of our system, we developed a gesture-based paint application using our framework. The tools and settings of this app are controlled using gestures, maximizing the user's painting area. In this application, the user input is almost always ambiguous because it is unclear when the user intends to gesture, paint, or move other objects. We show how the framework allows the application to resolve ambiguity and provide necessary feedback largely without requiring developers to think probabilistically. All logic related to uncertain input is actually handled within the interactors, which are in turn written largely without regard to probabilistic input themselves. The paint application itself mostly consists of standard code. It is made up of a canvas interactor, buttons to select color, and stamps, which are movable buttons that allow users to add images to their paintings. Our application also supports shake to undo. Each of these interactors uses our framework to monitor their uncertain state, provide feedback, and execute application action. To implement an interactor in our framework, developers specify a state machine description, something they would implicitly encode anyway. This state machine is completely deterministic, indicating events that prompt transition and what actions or feedback should be executed when making these transitions. For example, buttons in our implementation have two states, a start state and a down state. On the down-up transition, our button executes an action which invokes its onClicked event handler. This demonstration highlights the state distribution for each button. The buttons in this demo change the application background color when clicked. Notice that when the user presses completely over the button is in the down state. However, this is not the case when the user is partially over one or more buttons. The system tracks the interactor's uncertain state without requiring the developer to write any probabilistic logic themselves. When input is ambiguous, our system prompts the user to disambiguate. The developer, however, need not worry about this. When input is ambiguous, developers may want to provide feedback to indicate this ambiguity. Stamps, which are movable buttons, have three states to reflect this. When moving, stamps provide feedback indicating the system's confidence in the move. If multiple stamps might be selected or moved, each stamp changes its transparency to reflect the system's uncertainty. As in previous work, our framework allows developers to create interactors such as the resizable box seen in this video, which respond only to horizontal and vertical motion depending on how they are being resized, allowing for icons underneath to be dragged out. This demonstration illustrates how the user's horizontal and vertical motion changes the internal state of each interactor. Sometimes, as in the case of gesture recognition, the recognized input is the primary source of uncertainty. The canvas interactor reacts to drag or paint events as well as gesture events. Not only is it unclear whether a user is painting or gesturing, but it is also unclear which gestures the user is performing. Our canvas implementation has a state for each possible gesture. As the user completes the gesture, their input becomes less ambiguous, which is reflected both in the interactor state and feedback. Our framework allows developers to simply combine these interactors using basic application logic to create an application which appropriately handles ambiguity, not just within interactors, but between interactors. It just works. When a user accidentally grabs a stamp while gesturing, the canvas and stamp work in concert to show appropriate feedback and prompt the user to continue gesturing, whereas a conventional input system would have forced the user to restart. By using a sample-based approach, our framework enables complex interactions which handle ambiguous scenarios largely without requiring the developer to think probabilistically.